right, my friends.
It's hard to read clocks.
If you need more time, what's that? What's that?
I was like squinting at the clock, and you made a face at me. These kinds of clocks are hard for me to read.
Which ones? Oh, you like the
Want the
digital,
analog
like
clocks.
Okay.
I didn't learn how to read them until like 4th grade, and so it still kind of confuses me sometimes. But okay.
Wow. Cool. Thank God we don't use sundials. completely screwed. All good. So, if you need more time on the homework, take that time, understand it. That's what's important. There's a lot of little nitty-gritties in there. Remember, you can always check yourself. So on that one, what problem was that, Ella, you were asking me about?
14.
Yeah, so in 14, after you do all this stuff and you create some god-awful looking thing, you can check to see if it's right. Because you've got some points here, like maybe you picked 4i and you're sending that to 4 or something like that. You can just plug that in. You replace your z with 4i and see if a 4 comes out. So you can test to see if it's doing what you built it to do. And if it doesn't, something's wrong and you gotta debug. That's it. Is there any things I can help you, any general questions? If you've got some specific stuff, maybe we'll end a little early and I can help folks because I know there's folks who need consultation. We good? Okay, next Monday we have a quiz. It's up in the calendar. So next Monday, we're gonna have a quiz, and honestly, there's a couple theorems in there that I don't remember the numbers of, but they are in the calendar item. But the main thing is there's going to be a problem, and I'm going to give you a Mobius transformation T of Z, and I'm going to ask you to put it into normal form. That doesn't make sense yet, unless you did the reading as I begged you to do. I'm not making eye contact, I will not even look. So write in normal form. Find the fixed points, step 0, find the fixed points, we can do that. Write in normal form, which step 0 is essential to do. And this normal form will actually expose a hidden structure of the Mobius transformation. And so then step 2 is going to be classify the transform. And there's going to be 3 things it can be. It can be elliptic, hyperbolic, or loxodromic. Check that word out, right? Like new math word, I'm just like, it's got an X in it, sweet. Loxodromic, very cool. And if you did the reading, you probably know what loxodromic is, but I'm not going to ask right now. I think like a couple of things are a type 1 and type 2 Klein. Know what those are. Please know what those are by Wednesday. Type 1 and type 2 Kleins. It's like literally the first paragraph of the section we're in on more about Mobius transforms. Does that all sound reasonable? And yeah, and I give you, there's a practice problem that I'll write solutions up for. I think it's problem 1 in that section. You're going to want to work through that. So I'm just going to get right into the guts of what I want to show you today. Cut it out early and help some folks taking a look at debugging some things. And there should be plenty to do because you can start working on normal forms. So first off, let's recall something. And I'm going to ask someone to recall this for us. A Mobius transformation X form T of Z fixes 0 and infinity. So it's got 2 fixed points. The most fixed points you can have, right? There's either 2, or there's 1, or there's none. fixes, or all, excuse me, there's either two, one, or all of them are fixed. Fixes 0 and infinity if and only if, what does it look like? Oh, Ella, hi, yeah.
Like if it's just a rotation or
Keep going,
there's
yeah.
something else, scaling or?
Yeah, damn, that's so good, thank you. Oh my God, that's just, I was already in a good mood. I'm in an even better mood. If it looks like this is just a complex number in polar form. There's the scaling, the dilation that Ella mentioned, and here's a rotation. This is an if and only if, so if it looks like this is true. If this is true, then it looks like this. They are equivalent. That's really important for today. So now what we're going to do is talk about about normal form for a Mobius transformation T of Z with two distinct fixed points. This is actually really cool, and I think I actually understand it like I did, in December, and this is one of the things that freaked me out, but it doesn't freak me out anymore. It just fills me with joy. With fixed points, P and Q, and P is not equal to Q. That's the word and there. So what that means is that T of P is P, T of Q is Q. That's what it means to be a fixed point, so we know that. Let's throw in a new transform. So let S of Z equal Z minus P over Z minus Q. Very simple Mobius transform. Help me out here. Maybe Christian can help me. What's S of P, my friend?
S of P is 0.
Beautiful. What's S of Q?
Infinity.
Solid. Cool. So this S sends P to 0 and Q to infinity. So hey Camila, my friend, what does S inverse do? If this is S,
Infinity to Q
solid.
and 0 to P.
Beautiful, thank you so much. So S inverse does the reverse. It sends 0 to P, and it sends infinity to Q. And we know how to compute that inverse, right? We have the formula for doing that. We could write that up pretty easily if we wanted to. Awesome. So let's stack together S inverse, and T in just the right way. And this is really cool. This is so freaking amazing. So, what I want to do is combine T, S, and S inverse in a way that I have a transform, bless you, that sends 0 to 0 and infinity to infinity. So I'm going to create a new thing that does this for some reason. And you'll see how cool this is in a minute. So notice that S inverse would be the thing that I want on the right. So I'm going to put S inverse here. And S inverse sends 0 to P, and it sends infinity to Q, just like Camila told us. And then I'm going to put a composition. That's a composition sign there. And I might need a little bit more space here. In the middle, I'm going to put T, because T is, these are the fixed points of T. So T sends P to P and Q to Q. Yeah. And then I'm going to use S. So then I'm going to apply S, and S will take the P to 0 and the Q to infinity. So what I've got is I'm creating a transformation that looks like this. S composed with T composed with S inverse, and that's of Z. What are its fixed points?
Zero and infinity.
0 and infinity. See this? Look. Put a 0 in here. S inverse of 0 is P. So this becomes P. T of P is P. S of P is 0 again. So this thing fixes 0 and infinity. So I've just built, so let me stop. Think about this because it's really important to follow what we're doing here. We introduced this S, and then we took its inverse and stacked it around T to create this new transform that fixes 0 and infinity. And I'm going to let that be this U of Z. So that's going to be, I think I'm just using book notation here. So this U of 0 is 0, U of infinity is infinity. How's this feel? Yeah, good. Did you have quite, Lou, yeah, sorry.
Why are we doing anything with T? It seems kind
Because
of
so what we're gonna do is we're gonna use this thing we just built to expose something about the inner workings of T.
Okay.
You'll see in just a second. It's like this little prism or like a rainbow will appear on the wall. It'll be awesome. Is this cool? Does everybody see how I've got you doing this? So what do I know about you, Kitra? If U does this, what must U of Z look like?
The R, E, the I, theta.
Hell yeah, the thing Ella gave us, that this U must look like this times Z. It's just some multiple of Z. Cool, let's summarize that on the left side. So S inverse of T of S of Z is this U, but now we're just gonna call it this. Yes, ma'am.
Does it matter if it's S inverse
Thank
of
you.
T or
Yes,
S?
it does. Yes, it does. Thank you. Good call. Yeah. How do we feel about this? Yeah? Okay. Now, I'm going to apply the function S to the right side of each. So I'm going to compose S of ZS, right compose S. So in other words, I'm going to let this eat S and let this eat S. So these are functions. And so in other words, I'm going to insert a composition here of S of Z on this side and a composition S of Z on this side. And I can totally do that because S is a Mobius transformation. It is one-to-one and onto, it's got inverses, it's injective, bijective, if any of that shit means anything to you, this is a legit move. So I'm gonna compose S of Z over here. So this left side will become S composed with T of Z, and the right side is going to be this thing composed with S of Z. Well, think about what this function does. This is actually the U of Z, right? That's that U thing right over there. So what does it mean to say U composed with Z? So U of S of Z is RE to the I theta times just S of Z. So now that's not composition, that's times. And S of z has a very clear form, so this is just r e to the I theta z minus p over z minus q. So the right side becomes that. And let me actually move it in here a little bit better. So this is a crazy thing. I'll bet you've never seen anything like this. I'm not sure I've ever seen anything like this. It's magic. What's about to happen? It still doesn't look like magic. It doesn't look magical at all, but it will. What is this? Can you take a minute and simplify this? What does this left side look like? Think about, so this left side is S of t of z. Write out the formula for that. What is that? And once you do, we'll have accomplished our goal for today, besides talking about what to do with it and what it means. This feels like a real math class, you know? It's like some serious math going on in here. Oh, you're all fine, but thank you. Thanks for the haircut compliments, my friends. Thanks, I appreciate you. My wife cuts my hair now. It's great, I love it. I love it, because you know, she just gets real close. It's just very lovely. She gets close to me, she's standing by me, I can smell her, touch her back. She's just being very gentle and touching me. It's one of my favorite things in life. For the 2 haircuts I have per year.
Wait, so how did the, like, composition events just turn into, like, multiplying by s?
Because, so this right side, this was just u,
Okay.
right? And so I took u and I composed it with s on the right to get rid of that. And u, so this means this is u of s of z. But u is just multiply whatever's inside here by that r e to the I theta. Does that make sense?
Yeah.
Cool. Okay, I'm glad you asked, because I bet you're not the only one who wasn't quite sure. Nathan, do you have this left side worked out, my friend? This guy?
I'm still working on it.
Okay, cool.
Um,
It's okay. No pressure. Ella, you got it worked out? Okay. Grace, my friend?
Do we make equation for TUC? Just
No.
okay.
So all we can do
So
is
it's just okay, because I was like,
yeah, we don't know what T of Z is. It's some arbitrary thing.
perfect. I just did T of Z subtract P over T of Z subtract Q.
Beautiful. So this left side is just this. The right side is this. And this, my friends, is the normal form of T. And you might think, so what? That's what I thought at one point. Till I really thought about what was happening here. I don't think our book tells us enough to appreciate what's happening here. They tell you some really good stuff, but not the one thing I'm going to tell you. And that's how I finally understood why this helped us understand some things. So this is the normal form of T of Z, and only if you have 2 distinct fixed points. If T has fixed points, P and Q. My wife's constantly telling me, quit touching you while I cut your hair, I'm gonna cut your ear off. Okay. Stop. So, why is this important? Okay. So what is happening here? First off, I'm going to draw two planes. This is my input. This is my output. And the thing that links input to output is this Mobius transformation T. Notice the thing that's in common between the left and right sides are those fixed points, P and Q. So they're going to appear in each picture. They're essential to each of these diagrams. So let's say here's P, and then here's Q. Do whatever you want with them, honestly. Put them wherever you want, just make them distinct. And in the same place in both planes, because they didn't change. They're in the same locale. They're the same points in each place. Then, if I pick a point Z, say like right here. Now here I'm going to ask you a heavy question that I need you to think about pulling some knowledge together. What is Z minus PZ minus Q? So here's Z minus P. You can think of it as maybe that vector, like that. And I'm going to tell you, I think, because I thought about this a long time and it didn't come easy. So this is Z minus P, and then this is Z minus Q, kind of just viewing them as vectors. There's some little angle here. We could call it, say, alpha, and then these things have a length. So I could even express what I've just written here as the argument of Z minus P divided by Z minus Q. Remember, that's just the difference in their angles, so we could say that that's alpha. It's the angle between those two things. Remember how division of complex numbers, you subtract the arguments? So when you divide two complex numbers, you're subtracting the arguments, the angles that they create. So this is you can kind of think of that as this. Now look at what the right side is, the left side is. This Z gets moved somewhere. So it's T of Z. T of Z is somewhere else probably, but it's definitely somewhere else because the only things that don't get moved are P and Q. So it definitely got moved. So now over here, I've got T of Z minus P, and then I've got this vector, T of Z minus Q. And I've got some new angle between those two. So this is the left-hand side that I just drew. Here's the right-hand side. What is this saying about those two pictures? Geometrically.
Angle is the same?
That it's close. That this angle here is just a theta away from this angle. Right? So if the argument on these things is equal to alpha, then the argument here must be alpha plus theta. Here I would add these two arguments. So this angle here is that alpha over there, arg of this thing, is equal to alpha plus this theta. So in other words, what it's saying is that T of Z is kind of rotating that point Z by theta relative to P and Q. So this little picture here, this T of Z minus P over T of Z minus Q, is just this picture rotated by theta. Right? This is just a rotation. So this side is this side rotated by theta and scaled by R. Let me write that out in words, because I've been saying it all sorts of different ways. So we can think of this as T of z minus p over T of z minus q equals a scaling by a factor of r and rotation by theta. And this theta is something we'll be able to find. We're going to actually compute, we'll know exactly what r and theta are with a real problem. And we're going to do an example to see that. And rotation by theta of this quantity. So those fixed points give us an anchor by which to understand the way t is contorting the plane relative to these fixed points. That's about the best I can do on this. That was hard one. That was hard one thing. That took a lot of, just chilling with this stuff. But I think that that's a good way. It kind of tells you how t is twisting things in the plane and stretching them. It gives you a sense of that relative to its fixed points. So let's write that up too. Normal form gives us a measure of how t twists and scales relative to its fixed points. Now what I need you to do, I need you to do this. Read the stuff about type 1 and type 2 Kleins before Wednesday, please. Please, God, please do that. Yes, thank you. Thumbs up, indeed. Because if we all come in having pre-read that, it's just gonna help. Because what they say is way heavier than what I've just said. It's like starting to get like Joe Biden whispering and shit like that. Is that an old man thing? Maybe. You gotta read it. So, what does this tell us? And then we'll do an example. What does this tell us? Don't worry, I will never ask you to repeat what we've just experienced together. I just wanted to tell you that story. So, if the magnitude of RE to the I theta is 1, in other words, the magnitude of R is 1, there's no scaling going on whatsoever. There's only rotation happening. There's no rotation. There's no scaling. Only rotation. It's how we're being rotated that I need you to read about type 1 and type 2 Kleins. So we're rotating around type 2 Kleins. When you watch this, you might even want to watch this back after reading it again. We are rotating along type 2 Kleins. We are not moving along type 1 Kleins at all. This scaling, this is called a elliptic. T is elliptic. Think ellipses, think circles. Things are just spinning. There's no scaling. If the magnitude of R is greater than 1 and theta equals 0, theta is not equal to 1 because it could shrink too. If that happens, T is hyperbolic. And believe it or not, we're actually going to study geometry one day. Very soon. And the first geometry we will probably study is hyperbolic geometry. Elliptic geometry is the thing. This is where their names come from. So we're like literally at the cusp of geometry, which is insane. But here we are. We need like a whole other semester. And if magnitude, if there's scaling and there's rotation, it is called loxodromic. Your new favorite math word. It's definitely mine. It's a pretty sweet word. It's badass, right? Just even say it sometime in class. Say, ask one of your profs, your math profs, like, is that loxodromic? Even if it doesn't make any sense. And watch their brain spin. I think everybody's taught geometry, so they'll know what you're talking about. Okay, let's do an example. So, on the quiz on Monday, I'm going to give you a t and ask you to put it into normal form. Here's how you do that. I don't know why I'm staring over here. Example. Right? T of z in normal form. And this is fun. Who was telling me they really liked the maybe it was Ella was telling me you really liked all the computation in this class. You're going to love this. Write T of z in normal form. So let's say T of z equals, this is the easy kind to do. There's just a z on top, and then let's say there's just z minus 4 on the bottom. So put this in normal form. What is this thing doing? Is it elliptic, hyperbolic, or loxodromic? We don't know until we do this. Step 1, find the fixed points. Could you do that, please? It'll work out lovely. No ghastly quadratic formula action to be had. Bless you.
Thank you. How are we feeling about these fixed points? Works out, they're sweet, right? This is when this top, the one thing I was realizing while just thinking of examples was if the top is z, this is pretty hard to go wrong. You can always work it out without, there's no constant term, which is where things would get really horrible quadratic equation-wise. So if we agree our fixed points are 0 and 5, so pick whatever you want. P is 0, Q is 5. Write it in this form next. And literally don't put T, don't write the formula for T, put just the symbol for T. T of z minus 0 over T of z minus 5. P and Q are interchangeable. It doesn't really matter what order they are in. So you can't go wrong as long as it is consistent across this equation. And then here we have RE to the I theta. And then here we're gonna have z minus 0 over z minus 5. All that's left to do is find this. So step 2, I guess this is step 2, write out the skeleton for normal form. And we've done that. Step 3 is find that r and that theta. To do that, we just pick any point we want. Pick any z you want, except the fixed ones, which are gonna not give you any information. If I pick z equals 0, I'm gonna get a 0 here and a 0 here, and that's not helpful. So pick any non-fixed z. Go for, make your life simple. I'm not gonna pick 5, I'm not gonna pick 0, I've only got like a gajillion other options, but damn isn't one nice. So I'm gonna let z, when you can pick 1 or 0, do so. So I'm gonna let z equal 1, I just chose that. What is t of 1? Plug that in there. Plug that z into the right side. Hey, take a minute and do this, please. Let's do this together. So t of z, what is t of z? Negative a third? Let's see what we can do. Now this part might look gross because I just made this shit up. So I think like that r and theta could be nasty. We can do it. We might need an arctan or something, who cares? It's all good. Our main concern is r 1 or not, and is theta 0 or not. Kind of wishing I'd picked a number that didn't give me a fraction like this, but I don't even know if that's possible. I feel like z equals 6 would have been a good one. Oh, z equals 6 would have been sweet, right? Because t of 6 is 3. Oh, wow. So pick sweet numbers. I guess 1 isn't always the end-all be-all of everything.
Wouldn't it just be 1 minus 0 and then 1 minus 5 for the right hand side?
Thank you. Yep. Thank you, Lou. Cool. Yep, it's the z. Good stuff. Thank you, my friend. Life became suddenly less miserable. Oh, and then this side, I'm just gonna multiply top and bottom by -3. Hey, that's not all that bad, right? Isn't that just -1/4 on the left? Yeah, that's not bad. That's good. That's cool. So now you gotta go back. Everything we've done actually had a purpose. Believe it or not, this is like day 1. Convert that number into polar form. Here's -1/4. What's r? What's theta? What is r, by the way? Oh yeah.
Why didn't we just get rid of that 1/16, the left-hand side?
I multiplied both sides by this, that z minus 0 over z minus 5 became -1/4. And so I multiplied both sides by -4.
Okay,
And this was 1/16 to begin with. Yeah,
okay.
awesome. So r is a quarter, right? That's just the magnitude of that number. And what's theta? Pi. Classify it. What is it? Elliptic, hyperbolic, loxodromic.
Loxodrome.
That is loxodromic as hell. Yeah. There's some scaling. There's some rotation. So T is loxodromic. And that's what will be on your quiz next week, this process. You've got 3 problems to check your skill with, develop your skill. I'll write full solutions ASAP. But please work them before you look at the solutions, you know, I don't have to tell you all that, you know this. You've made it this far, you know how to do school. That's it for today. I'm gonna hang out and consult. If you wanna work, stay and work, I'll be here. If you don't, split. All good, whatever you need. We'll shut the recording down. Except for me.
Yeah, I think
It's
it
so
was the last
beautiful.
problem, so.
Wait, okay, so hold on.